microphone. Thank
you. Okay, it's my pleasure to introduce Professor Duong Phong from Calabi-Yau University. He will talk about supersymmetric string vacua, is that how it is? With torsion and geometric flows.
Thank you. So first, I would like to thank the organizers for the invitation to participate in this very nice celebration of JDG. So today, I would like to talk about a particular system of partial differential equations, which arises from string theory, but may be quite interesting from the point of view of complex geometry as well. So this system is sometimes called the whole-Strominger system. And let me try to describe it in some detail, and we gain some familiarity with it. So the setup is this. We have a three-dimensional compact complex manifold equipped with a nowhere vanishing holomorphic 3 form. So the first Chern class is 0, and we also have a holomorphic vector bundle over this manifold. So in 1986, right, Chris Hall and Andrew Strominger proposed independently the following system of equations. So in this system here, the unknown is a Hermitian metric on the manifold and a Hermitian metric on the bundle, which is denoted by H like this, and satisfying these three conditions. So let's sort out the notation first. First, by these upper 2002 and so on, we are indicating the various components of these forms. Right? So for example, 1, 1 is a 1, 1 form. Now the next thing is that in these expressions here, you see expressions such as Riemannian and F wedge F. So what these represent are the curvatures of the metric, right? Riemannian curvature metric omega, and F is the curvature of the metric on the bundle, and they are viewed as 1, 1 forms valued in the endomorphisms of the corresponding bundle. So in this operation here, what we are doing is that we are wedging the forms among themselves, but at the same time, because they are valued in the endomorphisms, we are composing them and taking the trace afterwards. So this is a kind of familiar things that one does when one deals with characteristic classes, and this is actually where these things come from. Now, you see another expression here, which is the norm of this holomorphic 3 form with respect to the metric omega. So because this is a holomorphic 3 form, there's a simple way of writing the norm, which is simply omega wedge omega bar times the inverse of the volume. So this is the invariant form. And then you also see a parameter, which is the slope parameter. In physics, it's positive, but let's leave it open for the moment. Right? The key thing is that it's constant. So what's the origin of these three equations? So roughly, the first one is something that is familiar to us. It's the Hermitian Yang-Mills. Right? The first two conditions simply mean that this connection that we are taking is a Chern connection compatible with the complex structure. And the last equation says that this is actually the Hermitian Yang-Mills equation. Of course, this equation depends on omega. So strictly speaking, you have to view them together. But there will be situations where in some sense the class of omega is known, and you can view this as an equation itself for the metric. The next equation is perhaps the most striking from the mathematical point of view. It actually originates from string theory, and it's a famous anomaly cancellation due to Green and Schwarz. So let me not go into this, but just pick out the feature of this that is of particular interest to us, to which I will come back very often, which is that it's actually a condition involving the square, right, of both curvature tensors. And then the last condition is one can interpret this as some kind of torsion condition, right? So if one writes it more explicitly, what this means, if you have a Hermitian metric omega, you can take a partial d of it, and that's the torsion. And this condition here can be rewritten like this. Now this torsion here is a 2-1 form. So if you contract two indices, you are left with one index, and that's the equation is simply that contraction is the gradient of the log of this norm. Right? So here are then the three equations, Hermitian Yang-Mills, anomaly cancellation, and torsion constraint. Now, one feature in this is that, as you see here, we are writing dd bar of omega. So that means that we are not necessarily considering Kähler form. Right? So because omega is not necessarily Kähler, there are many unitary connections associated with it. Right? The most familiar one is the Chern unitary connection, right, which is characterized by the fact that it's unitary, and the derivative along the bar direction is just the standard dj bar. Right? So the moment you have this other component is dictated by unitarity. So, and of course, you can then define the curvature tensor, and it's rather easy to work out this formula. And we do the same thing for the holomorphic bundle. Now, however, there are other connections. So there's one that appears in the literature, right, which depend on a parameter kappa. So the way you can think about it is that you can take the Chern unitary connection, and then you can correct it by adding a torsion term. Right? And that you can add by a parameter kappa. And now it seems that this formula was used rather often in the physics literature, where they refer to an old book of Yano, and it was subsequently redefined, rediscovered by Bismuth. And different values of kappa are interesting. So kappa is a half is the so-called Lichner-Rovich connection. So as shown by Chris Hall, the anomaly cancellation does not require a specific unitary connection for omega. So due to that, one can contemplate looking at this set of whole Schrodinger systems for Chern unitary connections, but also for connections of this form. So we are going to be concentrating the case of Chern unitary connections, and we discuss only rather briefly, right, one example with this kind of Yano-Bismuth connection in the case of unimodular Lie groups, and this was the case that was first suggested by these authors and then solved by Tangfei and Yau. Right? So I'll say more about that when time comes. All right, so that's our system of equations, and perhaps it's instructive to see how the famous case of Calabi-Yau manifolds can fit into this scheme. So in fact, this is what was written. This whole Schrodinger system is a generalization of a system of equations proposed by Candelas, Horowitz, Schrodinger, and Witten for compactifications of the heterotic string which preserve supersymmetry. Now, the way you can see this is the following. Let's take one solution, which is the case of Y Kähler, and then take this bundle to be just a tangent bundle, in which case you can take the metric on E to be the same as omega. So because it's Kähler, you have d omega is equal to 0. This condition here implies immediately Riemannian is equal to F. And the second equation, the tough cancellation condition, automatically is satisfied. Now the first condition just becomes the Ricci, and so you just have to solve the equation Ricci is equal to 0. And so this is the famous Calabi conjecture proved by Yau, that this condition is enough to produce such a metric in any given Kähler class. And now finally, from the definition, the Ricci curvature is dd bar the log of a section, omega square. And so this condition implies that this is constant. So if this is constant, it's rather easy to work out the dagger omega, and you find that it is 0. So all three conditions of Schrodinger system, whole Schrodinger systems are satisfied. So a Calabi-Yau manifold is a solution of this, and we can think about this as a kind of trying to generalize these solutions. Now, I mentioned quickly the origin of the whole Schrodinger system from string theory, but potentially they are of interest in math as well. There are at least some pretty obvious reason. The first one is that this set of equations perhaps can be interpreted as a kind of canonical metric in non-Kähler geometry. The reason is that in Kähler geometry, a so-called canonical matrix is typically defined by a kind of cohomological condition, such as d omega is equal to 0, and then by a curvature condition, such as omega has constant scalar or Ricci curvature. So this is a kind of linear equation in the curvature, and the analogy becomes obvious the moment you find out about this key observation of Junli and Yau, which is that the third equation, as I wrote down earlier, is actually equivalent to this condition here. Now, without this factor here, this is the notion of balanced metric introduced a long time ago in 1981 by Michelson, right? And so this is a kind of conformally balanced metric, if you will. And one could argue, and it appears that the notion balanced metric is quite natural because it was proved by Alexandrini and Bassanelli that the existence of such a metric is actually invariant under birational transformation. So it is a natural geometric concept. Now, the second thing is perhaps more PD-oriented, as will be most of this talk, right? So that it's interesting that we have an equation that involves the square of the curvature. So this, as far as I know, has not been studied as a PD condition in geometric analysis, and so it's clearly quite interesting from that point of view. And then the third reason is perhaps a bit technical, but on the other hand, I think it's a good motivation as well, because we'll see that for this whole Strominger system, although it's an elliptic system, there are good reasons, compelling reasons for viewing it as the fixed points of a geometric flow, so to adopt the parabolic approach. And so this is a quite novel kind of flow because it's a flow of two forms. And we are going to see that despite the fact that the motivation seems to be quite different and we seem to be coming from a completely different angle, it turns out to have some strong resemblance with the Ricci flow, although it's more complicated. So it's, if you wish, one could argue it is the next continuation of the Ricci flow. All right. Now, what do we know about solutions? I mentioned the very special solutions of Calabi-Yau earlier, and I should say that by now, a very large number of solutions have been found from either perturbations of known solutions such as Calabi-Yau, by duality constructions from string theory, in highly symmetric situations such as the case of Lie groups that I mentioned earlier, or by geometric constructions, building on earlier geometric constructions of Calabi-Ekman and Calabi-Gray. I would like to mention especially one very recent development, only about a couple of months old, which is the construction of a young group, Tang Fei, Sébastien Picard, and Jie Huang from Colombia, right, who Tang Fei was actually a former student of Yau at MIT. Who constructed actually an infinite number of solutions, which are non-scalar fibrations of Riemann surfaces. This is remarkable in itself because although lots of Calabi-Yaus are known, it was the issue of finding an infinite number is still a tough case, restricted to those. Now, but from our point of view, so this is actually the main motivation for this talk. From our point of view, the inspiring work is the one of Fu Yao in 2006. What they did is that they found, as you can see, some 20 years after the original equations were written by Hall and Strominger, they found the first non-perturbative, non-scalar solutions, and it was by PD methods. And the solutions was found on certain toric fibrations that were constructed by Goldstein and Pokushkin, and building on earlier ideas of Calabi and Ekman. So I'll say more about this when time comes, but the key thing is that in that case, in this setup, this system actually can be reduced to a single nonlinear PD of Monge-Ampère type on the base, which is a K3 surface, an equation of this type. Now, let's take a quick glance at this. The unknown is a scalar function u, and in 2 dimensions, this is the Monge-Ampère determinant of u. But there's these additional terms as well that will involve the Laplacian of u. So this will turn out, as you will see, to be a kind of Monge-Ampère, but with a shifted background that depends on u. But in any case, it's a novel, new type of Monge-Ampère, which is turned out to be quite hard. And it was rather amazing that Fu and Yao were able to solve this equation and to show that the existence of solutions is equivalent to the very simple integrability condition on mu. And again, here they did it for alpha prime positive and negative in 2 different cases, and using 2 different kinds of proofs. All right. Now, our goal is to try to develop a kind of method with which we can approach these problems a little bit more systematically. right? So as I had mentioned before, let's assume, cheating a little bit, that we can solve the first equation, which is the Hermitian-Yang-Mills equation, by, let's say, the theorem of Donaldson-Uhlenbeck-Yau. Right? So that means that our system will reduce only to a system of two equations for the metric on the base. But the problem is that there it has to satisfy, this unknown metric has to satisfy two conditions, namely the second equation, which is the anomaly cancellation, and the third equation, which is the conformally balanced. So how can one try to solve this system? Well, we can try to inspire ourselves a little bit from what happened in the Kähler case. So what one could possibly perhaps do is that one can pick out a balanced metric, something or conformally balanced to begin with, and then one can try to deform it in a way that preserves this conformally balanced. And among those deformations, try to solve for one that satisfies the other equation. In effect, that's what one does for Kähler metrics. Because if one looks for Kähler metric, one picks a reference metric, which is Kähler, one deforms it by a potential like this, and one tries to rewrite one's equation as an equation in U. Now, in our case, this balance conditions is a lot weaker, right? And it's a little bit still very unclear how best to deal with it. But if we try very naively to imitate this process, start from something which is balanced, right, and then correct it into something else that may be balanced, then this is the natural thing. You take omega squared and you add IDD bar of something, but then the very fact that this something here is a 1-1 form allows a lot of choices. So for example, you can take a scalar function u, you can take any function, any form omega tilde, and still have a balanced thing. And so it doesn't look natural, and perhaps worse than that, if you try to rewrite the equation in terms of these new unknowns that you introduce, you're going to get a very messy equation, right? So what to do? So this is what the main topic of this talk. So for now, I'm going to report on joint work with Sébastien Picard, who is a student at Columbia, and Jiangwen Zhang, who was a postdoc there and who is now at Irvine. So our goal, as I had mentioned, is to try to solve these equations in a more systematic way. And the idea we are suggesting is actually exceedingly simple, is to consider a flow, right? And now what flow? Our unknowns are omega and h, and so we are going to flow by these two flows, who clearly the stationary points of the flows just give you the equations that you want. And the advantage of this flow here is that, as I had pointed out, this is in analogy with both Chern theory, this is a standard that this form here is closed, right? So if you start from a metric which is conformally balanced, so that this thing is closed, and you evolve it by something that is closed all the time, so these will stay, d of this will stay 0, and hence you are preserving the conformally balanced condition. So that's automatically comes in without you having to pick any kind of ansatz. And so one can think of various versions of this, because, for example, if you think about the h as known, then of course this is known and that's one flow, or else you can think about this as a system. So let's call them generically as anomaly flow in reference to this Green-Schwarz anomaly cancellation. So here we are defining then a flow of omega and h as a matrix. And when it comes to flows, the first thing we have to worry about is, first, is it well defined or not? And then second, do we have at least short time existence, leaving long time existence for future work? So the first thing is the following, is that indeed this, although you flow a 2-2 form, you can recapture from that a flow of the metric omega. In other words, this vector field here defines a vector field on the space of forms. Now, as I had mentioned, the very fact that this is closed tells you that the balance property is preserved. Clearly, the stationary points are the equation, the whole Schrodinger system. And now the only thing which is left is to worry about is to check for at least a short time existence. So it turns out that if alpha prime by the Riemannian metric of omega as the initial data is small enough, and you can see that that would help here, then this flow is going to be weakly parabolic and will exist for a short time. Right? So let me just say that the key thing in going from 2-2 forms to 1-1 form, homogeneously in n-1 and n-1 to 1-1 form, is this key work of Michelson back in 1981, right? Where she showed how to go between these two. And in fact, one has this very simple formula, although it's deceptively simple because the star operator depends on the metric itself, right? So this is kind of a nonlinear thing. And then, as I mentioned before, right, one of the things that we need to do for the short time existence is to show the weak parabolicity, which does indeed hold. Okay, now what's the next thing? Well, the moment after you have short time existence, of course, your goal is long time existence and hopefully convergence, right? That's and for this we are going to need a much more detailed analysis than this previous theorem that required some very simple formal steps. And there, at the beginning, one could be a little bit concerned that these flows are going to be prohibitively messy, because the fact that, first of all, as I had mentioned, you have to deduce the flow of the metric from this. We know that can be done, but what kind of formula does that give? We don't know as yet, right? And then the second thing, which is always an annoyance whenever you deal with metrics which are only Hermitian and not Kähler, it means that that implies that you actually have a single notion of curvature tensor, but you have a whole bunch of notions of Ricci curvatures and then of scalar curvatures. Because in all of these, you can contract, right? You can always contract two of the indices, but which two, right, will give you different answers. Right? In the case of Kähler, they're all the same, right? So we are a little bit concerned that there could be a kind of proliferation of curvatures, but it is here, right, a very simple observation that this torsion condition that we work with and which we strive so hard to preserve is going to help us and simplify these things. So the very simple observation is that this conformally balanced condition, which is preserved by the anomaly flow, turns out to imply these relations. So that means that among these four Riccis, you can see that you have three of them are essentially the same up to this very subtle 1/2 that comes from the conformally balanced. And then you can go from one to the other, right, among these by the divergence of the torsion. And then mercifully, up to, again, the subtle factor of 1/2, all scalar curvatures are the same. Right? So with these things now become a kind of manageable, and so we can work out the following very simple theorem. Right? So let us consider the anomaly flow with a conformally balanced initial metric. Remember that it's key, right, to preserve this conformally balanced condition. And so in that case, you can rewrite the flow in a much more familiar form. Namely, you give how the metric evolves with time. Right? And the formula is here, right? And let me just sort out the notation. This R tilde here is this particular Ricci tensor, Chern-Ricci, right? And then T here is the torsion, and then phi here is the trace of F wedge F, whatever contributes is contributed by the holomorphic vector bundle. And over here, you have different sets of indices, and brackets means that you anti-symmetrize, which is what you would do because of these wedge products. Now, so this looks like a big formula, but it's instructive to compare it a little bit with a flow that we know quite well, right? So the flow I have in mind is the Ricci flow given by this, right? And now you see that if you compare the two, this term here looks like this, right? So this is, here it's Kähler, so it doesn't matter. These are like this. But the complication here is that, of course, we have this inverse term, we have torsion terms, and then we have these quadratic terms, which are perhaps the worst complication of all, right? So you can view this as a kind of Hermitian extension to the next order, if you will, of the Ricci flow. Right? Now, what's the result of these complications? Well, when it comes to a flow, the first thing that you have to work out is how do the curvatures flow, right? So in the case of the Ricci flow, I wrote down here some the simple formula. So they are essentially given by a flow with the diffusion term being the Laplacian, Laplacian written like this. And then for this, but then for the flow, due to these additional complications, not surprisingly, you now find this 1/2 omega. You have the delta that comes from this, but then you also have a bunch of terms that come from there, right? So automatically, the anomaly flow is more complicated, and in particular, the diffusion operator, right, which is kind of linearization of this, right, is going to have an additional term, which is a second-order operator whose coefficients are given by components of the curvature tensor. Now, the additional feature that we have to cope with is the fact that, of course, in the Calabi-Ricci flow, there's no torsion. So Calabi-Ricci preserves this, and torsion is 0 all the time. So when we deal with torsions, we are in completely uncharted territory, and it's easy to compute it out. Right, but here's the formula, and you see that this you have terms that are of the same order as the first term, and also that this Laplacian is actually different from the diffusion ones of the curvatures. So these are complicating features that make it hard to deal with in general. At least we will have to construct tools with which to address this problem. Now, the other thing is this: in the Calabi-Ricci case, the metric is changing by the Ricci curvature. So the cohomology class is just the C1 of y, and you see that along the flow, the cohomology class of the metric at time t is the 1 at time 0, and then minus t times C1. So this is this. So you have you're dealing here with a 1-1 class, and which is positive, right, as long as you have a metric in here. Now, the analogous statement is also rather easy to figure out, because it's rather easy to check that the right-hand side, the anomaly flow, is actually the Bode-Chern class for C2 of x minus C2 of e. Right? So if you flow by the time, here's the initial class, right? And then you change it by this time, right? But now the bad thing, which kind of hopefully things will improve when we understand these things better in the future, the fact that we have the 2-2 form, which is positive in the sense that it has a representative, which is positive, seems to provide a lot less information than the positivity of a 1-1 form. And this is one of the things that stand that is a difficulty in trying to understand the flow. And then also, although we have these flows of the classes, it'd be very nice if we can pick a canonical representative along each class that we can whose flow we can study. So, for example, for the Calabi-Ricci, you pick the potential, and then that will evolve by a kind of a parabolic Monge-Ampere equation. And this is a very useful, powerful tool. In this case, we don't know of a canonical way of choosing this. Right? In some sense, this is a manifestation of this problem at the beginning that one has to preserve the conformally balanced. Okay, so you can see here that there are many new difficulties, and certainly we will have a lot of things to do. But for the moment, let me focus on the most immediate question. Right? So one question that was a worry for us for a while is that we are proposing here a certain parabolic flow whose stationary point is a Holzstrominger system, right? Solution of the Holzstrominger. But is this the right flow, right? Because what happens is that suppose that you want to solve an elliptic equation such as this. You could take this flow, right? So the solution is clearly a stationary point, clearly this, but you could take this one as well, right? So which one is better? Right? Or does it make any difference? Well, it turns out that in PDE theory, it's well known that different parabolic flow could behave very differently, and that this one here is actually much better behaved than this one. due to the concavity properties in the second derivatives. Now, and so usually when you try to solve an elliptic PD by parabolic method, you could say it's almost an issue of picking a regularization, right? But in our case, we don't have such a luxury, right? Because our choice of equation was dictated by the need to preserve this conformally balanced condition, right? So we don't have any more freedom. So due to that, it's particularly important to find out whether or not this is so-called, let's say, informally well-behaved. Now, what could be criteria for the behavior, the good behavior of a flow? Well, often the flow will develop singularities, and we would like simple criteria for when this happens. And also, suppose that we have solutions, we would like to have a good basin of attractions of initial data where starting from there you would converge to the solution and capture a solution. So this is an immediate question. And from this point of view, right, the news are reasonably good, right? So we can consider 3 special cases, right? And in each of these, we can figure out the answer. So the first case, perhaps one could say is cheating, because you take this key parameter alpha prime to be 0, so that you get rid of the second order curvature tensor. But even that is not trivial, because even you get rid of the second order terms, the stationary points will be given by this, and combined with the balance condition, this actually implies that omega is scalar. So actually, the flow in this particular case would be starting from a conformly balanced metric. The question is that will it converge to a Kähler metric? So that's and as a flow, it's not easy either. Now, the next case is perhaps the case which is the most encouraging. So this is the case where of this Calabi-Ekman-Goldstein-Pokushkin fibrations. So this is the case where the elliptic equation was solved by Fu and Yau using these Monge-Ampere equations that I mentioned earlier. So it's a very important test of whether or not this flow is a good flow, or whether or not in this case it will converge to this solution of Fu and Yau. Right? So can one recapture it that way? And the good news is that yes, it does. And in fact, in some sense, a little bit more robust than the elliptic techniques. Because in the elliptic techniques, one has to come up with different arguments depending on the sign of this slope, alpha prime, positive or negative. In this case, it turns out that the same arguments work for both. And then finally, this is just a simple toy model, if you will. I had mentioned earlier the case of unimodular complex Lie groups, where Tang Fei and Yau found some solutions. So we could take this as a toy model for figuring out how the flow would behave. And this case is obviously a lot more tractable, because by the invariance, the flow is no longer a PDE, but it's simply a system of ODEs. So there we can try to work out exactly and see what happens. And you'll see that actually the behavior is pretty tricky. So it may be a good lesson for the future. Okay, so let me now describe more precisely what we know now. So let's first deal with the case alpha prime is equal to 0. So we drop the second order terms in the curvature tensor, and the flow just becomes this, which, as you can see, is very similar now to the Ricci flow, and this is at least the theorem that, in some sense, tells us that that the criteria for singularities development are reasonably simple. So this is a typical theorem of the kind that if you have control of the curvature, then you have control of the higher derivatives of the curvature after a short amount of time. A typical parabolicity property. And in this case, because we have a torsion, it turns out that the right analog is that if we can control the Riemann curvature, the torsion and the derivative of the torsion, which is of the same order as the Riemann, then you can control it for subsequent times after a little bit of short elapse. And from this, it's well known that, that if you have this, then you can continue the flow as long as this property is not violated. And that means that, oh, I should say also that here, besides it, you also need a uniform lower bound for omega. So that means that you will have flow will exist as long as either this, this norm here converges to 0 at some sequence of points, or one of these goes to infinity. So, so what this means, well, we have in the sense of what? You don't want to have conditions that involve an infinite number of derivatives. Right? So this is only these derivatives. All right, so this is only the first step, right? But it's an encouraging sign. And now let me describe a little bit what happens with this Goldstein-Pokushkin fibrations solved by Fu and Yau in the elliptic case. So let me just say a few words about this. Essentially, these fibrations are constructed in the following way. You start from a Calabi-Yau surface, and you put on it a Ricci flat metric, and you have a holomorphic form, right? Normalized so that this is 1. And now if you have two more forms, omega 1 and omega 2 with this kind of harmonic conditions, then they construct toric fibrations, right? So y over x. So a fibration, the fiber is a torus. And the key thing is that this fibration has a 1-0 form satisfying these conditions. Essentially, d of it is 0, so that's very good. D bar of theta is not 0, so it's not holomorphic, but it is the pullback of something on the base. So it's not something which is much more complicated and depends pointwise on the fiber. And then having this, you now can construct a holomorphic 3 form on y simply by taking this holomorphic form on the base and wedging it with this theta. So it's kind of remarkable that this thing turns out to be holomorphic, even though theta is not. And now, how do you construct the matrix on this fibration? Well, you can start with the metric omega hat on the base. Of course, you multiply it by any positive function. That's still a metric on the base. And then you can pull it back upstairs. So that would serve as a good candidate for metric upstairs, except for the fact that it's going to be, of course, degenerate along the fibers. So to compensate for that, you add this theta wedge theta bar. So this is a very natural metric on the fibration. And it turns out that it is conformally balanced for any choice of EU. Now, so that's, and now we arrive at this, we're going to try to solve the whole Schrodinger system in this setup. So we look for this system, and let's pick a bundle with the Hermitian-Einstein metric with respect to omega hat. Notice that the Hermitian-Einstein equation is invariant under conformal factor. So the fact that you have that makes it actually the same. It's still Hermitian-Einstein with respect to these other candidates. And then, so the only condition equation left is to solve this anomaly equation, right, which is the equation upstairs. But in the key calculation, right, Fu and Yau show that this equation descends on the equation on the base, right? And so these are more complicated objects, mu and rho, 1-1 forms and 2-2 forms that can be constructed out of all this data. But the key thing is that it descends the equation on the base, and this is the kind of motion pair equation which I mentioned earlier, and this is the one that Fu Yau solved and showed that the existence of solutions is equivalent to the integrability condition. All right. So our question is that let us now take this kind of setup, right, where we know at least that solutions exist, and what will the anomaly flow do in this case? So it turns out that the answer is quite nice. If you consider the anomaly flow in this setup, and with an initial data of the kind of matrix that was proposed in this ansatz by Goldstein and Pokushkin, then this ansatz is preserved by the flow, and furthermore, the flow exists for all time and will converge to a solution of the whole Schrodinger system. One thing that I have to call attention to, and this actually began with the work of Fu and Yau, is that you have to start, in this case here, you have to start from the initial metric here, which is omega hat times some EU. In this case, we start from an EU, which is a constant, and the key thing is the constant has to be very large. Right? The reason for that, as you will see later, is that the size of this parameter here is some kind of scale that allows us to compare various quantities. Right? All right, so this is the key theorem. And as I mentioned before, it works in both alpha prime positive and negative, right? And in fact, from the PD point of view, it's also interesting that right, we are dealing here with the Strominger system, but because of this setup of vibrations on the surface, this flow here will come down to a flow on the surface. And not surprisingly, from the point of view of the ansatz that was proposed, it comes down to a conformal flow. So the metric is flowing, right, and there's this conformal factor, and you can recognize that it is essentially the contractions of the formula for the flow that we found earlier. So the scalar curvature, the square of the torsion, and then these various higher order terms in the second derivatives. And the theorem is then so that given this flow, it exists for all time, and it converges to a solution of this. Okay. Let me just say perhaps just one word to explain very quickly why this difference in the behavior of alpha prime positive or negative. So in terms of the scalar factor, as you saw in the previous thing, this is the Fu-Yau equation, right? So the elliptic equation is this, the parabolic is that. Now, why does this sign difference matter? Well, you can see it here. First of all, one reason this is tough is because this actually does not have good concavity properties. But let's try to see why the sign. You see that here you have a Hessian, and here you have some second derivative. So actually you have to put these together, and the way to do that is to write this whole expression as roughly the determinant of dd by u, but shifted by eu or omega hat. So the background is not omega hat, as you may expect, but it has to have this EU in there, right? And then you will have also additional terms involving the gradient of u to the square. And now you can see why things are different, because suppose that we impose the purity subharmonicity condition that this is positive, then you see that if alpha prime is positive, then you can control the du square easily, because this whole thing is positive, so therefore this cannot be that big. Right? Now, on the other hand, if alpha prime is negative, then this is very easy to bound, but the problem is that the determinant may slide to 0. So if you wish, in PD parlance, in one case the hard estimate is C2, the other one, the hard estimate is C1. Okay, so let me now say a little bit, very quickly, about how to prove this theorem. So the first thing to do is to show that the metrics in this flow are all equivalent, and this is one step, right, which is somewhat similar to the one used by Fu-Yau, in the sense that you make use of the equation in terms of the scalars, and then you use a Moser iteration. Right. And so here I state roughly what it is, and the key thing that you have to start from an M which is big enough. Now, after you get the equivalence of the matrix, the next thing you have to do is to deal with all the derivatives. So I don't have time to run over all of this, but let me perhaps single out a couple of ingredients. The first is this thing that I stressed all along, which is that when you look at the flows, the diffusion operator is no longer the Laplacian, but it is something that involves the curvature times alpha prime, clearly going back to the second order things. And you see that here you start with the Laplacian, but you have to deform it, right? This is a contribution to second order terms. So what one has to do, remember that for short time existence, you have to assume this. So the key thing is that will this condition be preserved along the flow? So that's where the hardest part of the work is, right? Now, the next thing, this is a mere technicality, but perhaps to be fair, I should say why is this Goldstein-Pokushkin case much easier? It's because in this case, it suffices to know the dd bar u to know the full Riemannian curvature, and you don't need to know the full torsion tensor, but only a contraction, because the full torsion one comes already from the contraction. So that makes it easier, and the nicest thing is that it turns out that the diffusion for both curvatures and torsions are the same. So that facilitates a lot the application of the maximum principle. Okay, so let me skip the rest, all these various bounds, right? And in order to say just a few words about the unimodular case. So this is the third case where we wanted to study the behavior of the flow, and in that case, right, it turns out that every metric on a unimodular Lie group is satisfies the conformally balanced condition, and so then let's just take the bundle to be flat, so the part about the curvature bundle disappears, and all we need then is to solve this equation. And so this is the one that Fei and Yau solved, and they found a solution of this kind, right? Where I forget, this is beta. I'm sorry, this is in a row. So the solution is proportional to the identity in this standard basis, and times a coefficient that you see depends on the parameter alpha prime as well as on this parameter kappa that is along the Gaudition line. And so you see that except for kappa is equal to 0, which is the Chern connection, and kappa is equal to a half, which is the Lichner-Ritz, then for anything on the Gaudition line, you do have a solution. And the key step in the arguments is that if you look at this equation, you can worry a little bit, because Riemannian is not a 1-1 form, but their key discovery is that this is still a 2-2 form. So let me now just say very quickly what happens. So we are interested in the anomaly flow, right? So let me write it like this with plus and minus. In the PD case, you have to pick a sign because you want the equation to be parabolic. But invariance makes it all ODE, so therefore you can pick either sign, right? And then you should look at them both. And it turns out that the flow, if you look for the initial data, which is diagonal, is given by this dynamical system. So it's a little bit non-trivial, but nevertheless, it can be analyzed. And this is what we find, that the stationary point, right, found by Fei and Yau is the unique one, right? So, right. Now this stationary point is hyperbolic with eigenvalues +1, and -2, so it's not asymptotically stable, right? Nevertheless, if you start from data which is proportional to the identity, then that condition is preserved and the flow will converge. Now, otherwise, it will diverge most of the time, because suppose that lambda, the higher, because eigenvalue is bigger than beta. So right, so that means that if you are close to the stationary point, this will surely happen, right? So and then if that happens and you have things that are not diagonal, then actually this ratio is monotone increasing. So that will tell you that you are actually being taken away from the critical point. And then, of course, we are quite interested in watching out for the role of the second order terms, right, alpha prime. And remember that this parameter beta here is proportional to alpha prime. So you can see that this sign plays a big role, because if this is negative, then the flow actually will terminate in finite time. So you see a very complex behavior depending quite a bit on where you start from. And clearly, we have to anticipate that in subsequent studies. So let me stop here.
Any questions or comments? Okay, if there is no question, let's thank the speaker again.